Hey everyone, welcome to our week 9 lecture. So today what we're talking about is correlations, correlational associations, correlational analyses. So where we're at in our term so far, we've covered a bunch of things. We're kind of at this just over halfway point. So you've covered a whole lot of t-tests were the first kinds of analyses that we talked about, and those were 3 different sorts of t-tests. And hopefully you saw with the t-test processes that even though there were different sorts of tests that we were covering each topic, we had the one sample t-test, the independent samples t-test, and the paired t-test. Even though there were different sorts of tests, that the processes of running an analysis, of doing a statistical test, was pretty similar between the 3 of them. And hopefully what you'll see with our correlation lecture here is that it's the same sort of a thing. So it's a different kind of an analysis, it's a different research question, but it's framed in the same way in terms of using stats to address psychological research questions. And the process that we go through in running our test and interpreting our test is actually the same as well. So what it is that we're talking about today. Start off by talking conceptually about what a correlation actually means. And a correlation might be one of those things that you've heard the word before as opposed to something like a t-test. You probably heard people use the word correlation in just kind of normal outside of academic contexts. So we'll talk a little bit about what a correlation is. We'll talk about the actual correlation coefficient, which is the number that we get from our analysis that we'll run that gives us information about the strength of an association. We'll also talk about assumptions. So just like with our t-test, every single statistical test comes with some assumptions that need to be met. And so we'll talk about what they are and how we check those. Some of them will be familiar to you. And then we'll talk about different kinds of strength of association. So how to tell if there is a strong association versus a weak association. We'll also talk about scatter plots. So scatter plots are the particular kind of graph or chart that we use to represent what is being tested in a correlational analysis. So a scatter plot is a visual representation of an association between 2 variables. We will talk relatively briefly about the actual formula that you use to calculate a correlation coefficient if you were so inclined to do so by hand. And I will be emphasizing to you that you guys do not need to know the actual formula and you don't actually need to know how to calculate it yourself, which is why we'll talk about it relatively briefly. And then we will actually go through working through a correlational analysis in Stata itself, so show you how to get the actual analysis in Stata and how to interpret the output. And then we'll finish off the lecture with some important conceptual points and some distinctions between what it means to have a correlation, to have an association between things, and how that is definitely not the same thing as a causal relationship, a cause and effect relationship. So that's a really important point, which is really important for thinking about the kinds of things conceptually that we're trying to test to see if they're related in contexts where we're running correlational analyses. And it's a really important thing to take away that there's a really big distinction and a meaningful distinction between something being associated with something else versus that one thing causing a change in something else. That it's not the same thing. So we're going to start off by talking about what a correlation actually is. So to start with, a correlation is basically a linear, which just means a straight line, relationship between 2 numeric variables. So you know all about what a numeric variable is. A numeric variable is something that's scored or represented on a numeric scale. Something where there's actually a numeric value, a number value that represents the value or the level or the score or the kind of particular point of that particular scale. So a correlation is just representing a relationship, but it's a specific type of relationship, which is a straight line relationship, a linear relationship between 2 numeric variables. And what that means is that you can represent the association, the relationship, using a straight line. And that will make more sense when we actually look at our scatter plots, because that's the visual representation and we can look at those straight lines and see how they're actually the representation of the association. But that's the technical definition, that a correlation is a linear relationship between 2 numeric variables. And to give you a couple of really common examples, or not common examples, but examples that hopefully make sense to you because they're things that you can easily kind of grasp and they're relevant to you. Let's say that I want to see if there's a relationship between the number of hours that somebody spends studying and their performance on an exam. Both of those things are numeric variables. Number of hours studying is numeric. You measure the number of hours, it's a number. An exam performance could be a number between 0 and 100 or between 0 and 50, whatever it actually is measured as. But that's looking to see if there's a relationship between those two variables. If you study more, do you then perform better? If you study less, fewer hours, do you perform worse? So is there a relationship between those variables? I could also see if there's a relationship between a love of movies and the number of movies seen in a year. So again, these could be numeric variables. Love of movies could be rated on a scale from, say, 0 to 10, 0 meaning I hate movies and 10 means I'm obsessed with them. And the number of movies seen in a year is a count variable, so it's a numeric representation. So again, is there a positive relationship? Is there an association or a correlation between love of movies and number of movies seen in a year? I could also see, if I was so inclined, to determine whether there was a relationship between somebody's sense of humour and the number of memes they include in a lecture. So I could have a hypothesis that people with a better sense of humour, a greater sense of humour, will include more memes in their lectures because they're hilarious and they make the learning experience so much more enjoyable, right? And so that could be my hypothesis, and I would test that hypothesis using a correlation. So again, two numeric variables, seeing if there's some kind of relationship between those variables. And correlational analyses, correlational tests, are really common for observational research designs. So as you know, an observational research design is contrasted, is different to an experimental research design. In experimental research designs, there's some sort of manipulation. There could be random allocation of the independent variable or just manipulation of the independent variable. Whereas in observational designs, there's no intervention on the part of the experimenter or the researcher. There's no changes being actually imposed on the participants. All we're doing in observational research is just measuring things as they naturally occur. And so in observational research designs, a correlation is not the only kind of analysis, but a very common analysis to use. So it's when we're not manipulating anything, we're just measuring naturally occurring scores or levels of something and seeing if two variables are related. So those were a couple of examples there. And on those examples on the previous slide, they were actually all examples of a positive correlation. So correlations can be either positive or negative. A positive correlation means that higher scores on one of your variables is associated with, is associated with higher scores on the other variable. So greater scores, a greater value on one variable goes along with greater scores, greater values on the other variable. So higher goes with higher and also lower goes with lower. So a positive correlation is also that lower scores on one variable are associated with lower scores on the other variable. So these were the examples on the previous slides. So higher number of hours studying goes with higher exam performance, just like lower numbers of hours studying goes with lower exam performance. Correlations can also be negative. So a negative correlation means that higher scores on one variable is associated with, goes along with, lower scores on the other variable. And negative correlations are also called inverse correlations. So they kind of go in the opposite direction. Higher on one variable goes with lower on the other variable. So to give you a couple of examples of that, let's say the greater the number of children that some parents have, the more children they have, the less sleep that their parents get. So higher scores on number of children, higher values on number of children, corresponds with lower scores, lower values on the sleep variable. It could also be the warmer the temperature, the less clothes that you wear. So the higher the temperature, the higher scores on our temperature variable, the lower the scores on the number of clothes wearing variable. And as I mentioned before, a relationship between two variables can be represented using a scatter plot. So a scatter plot is a visual representation, a graph or a chart that represents the actual relationship between these two variables. And a scatter plot is a really important thing to do to actually have a look at your data before you formally run the correlational analysis. And I'm going to say that a number of times today, that you perform the scatter plot before you actually get to the correlation running stage. So onto scatter plots. So a scatter plot is a graph that represents the kind of data that we perform a correlation on. So a scatter plot is a graph that has two axes, an x-axis, which is a horizontal axis, it goes from left to right, and a y-axis, which is our vertical axis that goes from up to down, or technically down to up. That's a demonstration of the two different axes in our scatter plot, the x-axis and the y-axis. And the thing that a scatter plot has is it has dots on the actual graph space itself, and every dot, every point on that graph represents an actual observation. So a person's score or an observation from our data set. If you can picture your kind of spreadsheet of data, every dot on this particular scatter plot is representing one row, one observation in your data set. And the location of that dot, where that dot actually sits in this XY axis space, reflects or is represented by its score on each of the axes, on each of the variables that are on the axes. So if we have two variables, which we always do for correlations, one variable goes on one axis and the other variable goes on the other axis. And then the score on that variable is reflecting where the actual point is sitting on that particular graph. So if you look at the example there, time spent studying is on our x-axis down the bottom. So if I'm somebody who spends no time studying, my point would be on the left-hand side of that axis. If I'm somebody that spends a whole lot of time studying, my point is going to be on the right-hand side of that axis. And the same goes for the y-axis on the top there. If you have, so say your two variables that you're actually representing with the correlation and the scatter plot here, if you have a distinction between an independent variable and a dependent variable, then the independent variable typically goes on the horizontal axis, the x-axis, and the dependent variable typically goes on the y-axis, the vertical axis. Note that that's just convention, that's just how people typically represent these sorts of things in graphs. It doesn't actually change any of the analysis itself, it doesn't actually really change the graph, it's just a conventional display thing. That if you have an IV and a DV distinction, the IV goes on the x-axis and the DV goes on the y-axis. So as I said, we have as many points on this graph as we have observations. So say we have 100 people in our data set and they gave us answers to a whole lot of questions, then I would have 100 points in this particular scatter plot. So what is a correlation? So a correlation is representing whether there is a clear association, but remember specifically a linear association, between two variables. So what you can see in this particular graph here with all of these individual red points, remember that each point is an observation. We're looking to see if there is a trend in this point cloud as we move from left to right. Does our point cloud go up? Does it go down? Does it move in a consistent or a kind of combined sort of a way, like a general trend? Can you see a pattern or a picture in this particular point cloud? And what we're seeing here is that there is a general positive association, a positive trend between time spent studying and student grades. And what that means is that for students who spent less time studying, which are represented on the left-hand side of the graph, they're the points on the left-hand side of the graph, the students that spent less time studying, they tended to get lower grades. So they were also down the bottom of the grades axis. Whereas for students who spent more time studying, they were up on the right-hand side of our horizontal axis. They're up over here, if you can see my mouse moving. They're on the right-hand side of the horizontal axis. Those students that spent more time studying tended to get better grades. So they're on the right-hand side of our x-axis. They're also up the top of our y-axis, which means they got higher grades. Their score on the grades variable is also higher. And this is representing a positive association. So that means that generally speaking, higher scores on one variable correspond to higher scores on the other variable. But note that this is not a perfect association. It's not a perfect, precise one-to-one association. What we're seeing is whether there is a general trend to a positive or a negative association. And if you can have a look where the yellow kind of rectangle is highlighting some dots there, if we just pick one point at the x-axis, doesn't matter what point it is, just any arbitrary point on our x-axis, there is a range of scores on the student grades variable. So there's some students, like this student down the bottom here, that got very low grades. There are some other students that got higher grades. even for about the same amount of time studying. So it's not a perfect association, it's not a one-to-one association, but is there a general trend? Is there a general trend towards positive scores, like higher scores on one variable, going with higher scores on the other variable, which means a positive relationship? Or is there a negative relationship to higher scores on one variable go with or correspond to lower scores on the other variable? There's always going to be variability. You're never going to get a perfect association. But what you're looking for is there a general trend? Is there a general pattern that we can see here? And so what we have here is our positive correlation. On the other side of the slide here, on the right-hand side, we have a depiction of a negative association. So what we have here is number of missed classes on our x-axis and exam score on the left-hand side on our y-axis. So it's on our vertical axis. And what you can see here is that for students who missed more classes, they tended to have lower exam scores, whereas students who missed fewer classes tended to have higher exam scores. That's the kind of thing we're looking for here. Is there a general straight line positive or negative association? So the left-hand side graph is representing a positive correlation, the right-hand side graph a negative correlation. If there was no association, if there was no correlation, then you might see something like this graph here on this slide. So this slide's representing an association where there's no clear positive or negative correlation. What we have here is health anxiety on our x-axis and loneliness, social loneliness on our y-axis. And you can probably see here that you can't really see much. So there's no clear positive trend, there's no clear negative trend. There's really no association going on. So this is representing no correlation. And what we can say is that as health anxiety increases, so as we go from left to right on the graph, or from about 0 to about 25, there's no consistent change in social loneliness. As health anxiety increases, social loneliness doesn't increase, social loneliness doesn't decrease, it doesn't consistently change. There's no consistent trend or consistent association. And that's what no correlation looks like. No correlation means it's just a random scattering of points. There's no positive trend, there's no negative trend, no association. And that's kind of also represented with our right-hand side image here. So what this graph is representing is the probability that you'll come up with a brilliant idea on your y-axis, the vertical axis, and then the time spent staring at your computer on the x-axis. And you can see that as time spent staring at your computer increases, that there's no change in the probability that you'll come up with a brilliant idea. So a very good demonstration of no correlation, no association. So if you've got